In this lecture, we'll see how we define the habitable zone. The habitable zone is a concept in astrobiology representing the range of distances from a star where a planet has the conditions suitable for life. Because of our presumption that life needs liquid water, this represents the distance from a star where the surface temperature is somewhere between 0 Kelvin, the freezing point of water, and 100 Kelvin, the boiling point of water. Now notice this makes some assumptions. First of all, that the assumption that water is essential for life, or liquid water. Second, it makes the assumption that no other conditions are essential for habitability. So it's a fairly simplistic notion. Third, by only talking about the distance from a star where the surface is at a particular temperature, it doesn't take into account any particular properties of the exoplanet, but we'll talk about those. So habitable zone has a traditional definition that I've just given, but astronomers and astrobiologists have experimented with variations from the habitable zone. The other huge assumption the habitable zone makes is that life is on the surface of the planet. Now on the Earth, the biosphere is indeed painted on the surface of the planet, although life does exist deep in the ocean and deep inside rock. And so the general concern might be that biology doesn't have to sit on the surface of a planet. And so this simplistic definition based on the radiation from a star might be inappropriate. But we'll start with this definition and see how far we can get. It also depends on the type of star, and we know there are stars of all kinds that have planets around them. So we should be generous in our definition of the habitable zone to include stars that are not like the Sun. And we can see how that might go in this diagram. Here is the traditional habitable zone in the dark blue, the range of distances where water can be a liquid. For the Sun, it's a logarithmic scale, notice, and the Earth sits squarely in the habitable zone. Mars is towards the edge of the habitable zone, and also Venus. Now, Venus is uninhabitable for the reasons of the runaway greenhouse effect. If you go from a star different from the Sun to a lower mass star, the luminosity is less, the radiation is less, and so the habitable zone shrinks towards the star. You can go all the way down to red dwarfs, the most abundant stars in the universe, and the habitable zone starts to get very close to the star. For these very low mass stars, what happens is that the habitable zone enters a region beyond this line representing tidal locking, which means the planet, especially an Earth-like planet, is so close to its relatively low mass star that it is tidally locked and always has one face pointing at the star. That itself may affect the habitability. So we do not have a good idea yet as to the habitability of planets around dwarf stars. Why does this diagram not represent stars more massive than the Sun? Because there are clearly stars 2, 3, 5, and 10 times the mass of the Sun. They exist, and their habitable zones accordingly would be further out because there's more radiation. They're taken off the table by astrobiologists for the simple reason that more massive stars have shorter lifetimes. By the time you're at several times the mass of the Sun, the total time the star is alive as a main sequence star converting hydrogen to helium is less than 1 billion years. We don't know how long it takes biology to form and become complex, but we think it's probably hundreds of millions of years at least. And so the most massive stars are uninteresting for astrobiologists simply because they live too short a time. Their lives are too short for interesting things to happen chemically and biologically. Also, they represent a small fraction of all stars, so we're not missing much in our census of biological sites by omitting the massive stars. What are the conditions we need for liquid water? Well, as I said, it's a simple temperature definition in terms of physics. The surface of the planet must be cool enough that the water is not steam, as exists in some parts of the Earth's surface, and yet warm enough that it's not permanently frozen. Notice water has a particular property, which is to say it expands when it freezes. This is very unusual behavior. Essentially no other common liquid has this behavior. That's potentially very important for biology and astrobiology because it means that, as we know, a large body of water freezes from the top down. And if it's very large, or moving internally like an ocean or a sea, it never freezes completely solid. And that means that the surface temperature can be much less than the freezing point of water, and yet liquid water exists under the icy surface. So this particular property of water, that it expands when it freezes, does expand the habitable zone slightly in the lower direction. Pressure is another feature that affects the conditions under which liquid water can occur. We've seen that on giant planets, the atmospheric pressure, the intense pressure at the base of their hydrogen and helium atmospheres, actually forces molecules into exotic states, like metallic hydrogen. It also forces water molecules into exotic states. And so we think that what is required for a habitable zone is that water be a stable liquid and not in any exotic and high-density state of matter. The conditions for liquid water are essentially determined by the distance of a planet from a star, how much energy it gets from the star, but also by the planet's mass. So the planet properties matter here too. The first part is easy to calculate. When we know the luminosity of a star, we essentially know how many photons it emits every second in all directions. Light carries energy away from a star in every direction, and the intensity of that radiation follows an inverse square law. You can think of light bundles traveling out through a region, and the number of light rays doesn't change, but they're more diluted or diffused as they move out from the star. This is the inverse square law. So when you're twice as far away from a star, you receive 1/4 of the radiation. 3 times away from a star, you receive 1/9 of the radiation. So knowing the intrinsic luminosity, how many photons per second a star is emitting in all directions, and then the distance you are to get to the exoplanet, we can calculate how many photons any square meter of a planet's surface is receiving from that star. The Earth, for example, at the base of the atmosphere, is receiving about 1,500 watts of radiation from the sun. So we can do similar or analogous calculations from exoplanets around other stars. So proximity to the star obviously is what determines the habitable zone. It's a Goldilocks concept. If the distance is such that the surface temperature is between 0 and 100 Kelvin, then water can exist on the surface, and it's just right. This is not a narrow band, this is a significant band because 100 Kelvin is a fairly good range of temperature. There's obviously a distance at which the water would be frozen, and then another distance within which the water would be vaporized, unless it's protected in some way. So this is the simple idea of a habitable zone. But we also have to consider what's happening inside the exoplanet, because the exoplanet is not just a passive recipient of stellar energy from its parent star. An exoplanet of significant mass, such as an Earth, an exo-Earth, or a super-Earth, will have an interior heat source, as the Earth does. Will have geological activity, as the Earth does. And so exoplanets that tend to be on the far end of their habitable zones, and so ostensibly too cold to have liquid water on the surface, could have liquid water if they're geologically active enough, which is to say massive enough, to add that energy into the mix. This energy comes from 2 modes. It comes from radioactive decay of atoms in the rocky material of the planet, and it also comes from volcanic activity. The volcanic activity itself produces heat, and also when the volcanoes penetrate the surface, tends to produce carbon dioxide, which is detached from the rocky material, the carbonates. So it is possible for liquid water to exist at larger distances from a star if the planet is massive enough. The other issue that relates to mass is the ability to retain an atmosphere. One of the simple assumptions behind the habitable zone is that the radiation is at the surface of an exoplanet producing a particular temperature. But the temperature on the surface of a planet is affected by the atmosphere that shrouds it. The radiation for the Earth passes through the atmosphere of the Earth, but the Earth's atmosphere is a blanket that contains greenhouse gases that warm the Earth. In other words, the surface temperature of the Earth with its present atmosphere compared to the Earth if it had no atmosphere is about 17 or 18 Kelvin hotter. So that greenhouse effect, which of course depends on the detailed composition of the atmosphere, is a significant warming effect. In the Earth's case, those greenhouse gases are primarily carbon dioxide, as we know to our peril with the rise of global climate change, and methane is the secondary greenhouse gas. We think other exoplanets may well have atmospheres, and of course they'll have their own greenhouse gases, and we have no way yet to know what the composition of those greenhouse gases are. So we're stuck with our more simplistic definition of a habitable zone because we can't calculate the impact of the atmosphere of an unknown exoplanet where it hasn't been measured on what the surface temperature would be. Either way, the presence of an atmosphere acting as both a protective shield against high energy radiation from space and as a thermal blanket, raising and stabilizing the temperature of the planet, can act to expand what would be the traditional habitable zone. So we can imagine some possibilities here. In this situation, we imagine a small planet that has sufficient mass to retain an atmosphere, but has very limited heating ability to maintain liquid water. So this would really be too cold and probably would not be a habitable. But if it was a super-Earth, the intense light with strong radioactive and geological heating might even evaporate the surface water. So you could have an overshoot where the properties of the exoplanet, which might allow liquid water to exist, are actually too strong and vaporize it, and so remove it from habitability. Again, these same strong internal heat sources could make up enough heat for the super-Earth to have liquid water if it was suitably positioned at the far edge of the habitable zone. You can see with all these issues to play with, the geological heating associated with the mass of the planet, the chemical composition of the planet, and in particular its atmosphere, and that impact with greenhouse gases, means we have too many uncertainties to be rigid in our definition of a habitable zone. Using these conventional definitions, however, we can look at the equilibrium temperature for a large number of exoplanets found with the Kepler spacecraft. Here are the sizes relative to the Earth, and as we know, Kepler has been quite adept at finding planets as small as the Earth or even smaller. And here are the calculated surface temperatures, equilibrium surface temperatures, again with no assumption of an atmosphere because we don't know the atmospheres of these planets. There's the Earth, there's Jupiter, and here is the classic habitable zone outlined in green. And you can see that there are a small number or a small fraction of the total exoplanet haul from Kepler where there are planets in the habitable zone, and a few are even close to Earth-like. Here's a different version of doing this using a slightly more generous definition of habitable zone, where it's acknowledged that geological activity and the most probable atmosphere for an exo-Earth or a super-Earth can indeed alter the equilibrium surface temperature. And so there's a sweet spot, the habitable zone, and then there are hot and cold zones where, depending on these properties, which are still unknown, it's possible that it could be habitable. And when you use this more generous definition, based on modeling of these extra factors, you could see that there could be hundreds of habitable exoplanets found from Kepler observations so far. Perhaps the most interesting of these, just discovered a few years ago, is TRAPPIST-1, which made the news headlines for a number of weeks. The TRAPPIST system is known to have 7 planets, and actually there are 2 more that haven't yet been confirmed. So this is 7 planets orbiting a single star. It's almost as rich as our own solar system. It's only about 39 light years away, which is relatively close for an exoplanet. Here are the Kepler light curves that identify the exoplanets by their transits, and you can see the data is very powerful and strong and incontestable. And in this diagram and in the properties that you can see here, 3 of these 7 exoplanets lie within the habitable zone of the parent star. So here, in one fascinating example, we have 3 habitable exoplanets that are not too dissimilar from Earth size in one exoplanet system. Very exciting. And this is just a sample, of course, of more to come, or what must be a very large population in the Milky Way. Let's look at the diversity of exoplanets that Kepler finds with 3 examples. A planet inside the edge of the habitable zone, a very hot planet, too hot for life to exist, maybe even molten at its surface. We're using visualizations of what the surfaces of these planets look like because we cannot see them in this level of detail and may never be able to. That's uninhabitable in the hot direction. Uninhabitable in the cold direction, beyond the edge of the habitable zone, is an ice giant planet, and we visualize what its surface might look like. Finally, the sweet spot, the habitable zone, an Earth-like planet. Not really the Earth and not a clone of the Earth, but habitable with liquid water on its surface. So we've seen that the habitable zone is a simplistic definition of life. It involves the assumption that liquid water is required, and it involves a temperature range of 0 to 100 Kelvin, where water can be liquid on the surface of a planet with no atmosphere. In other words, somewhere between water freezing and water boiling. In practical terms, however, the property of the exoplanet matter. Because if the exoplanet is massive, it will have geological heating, and that will add heat to the equation, and so increase the outer range at which a planet could be in the habitable zone. Equally, a massive exoplanet, a super-Earth, or even an Earth-like planet, will have an atmosphere, and that atmosphere is likely to have greenhouse gases and will have some thermal blanketing effect, and so raise the surface temperature beyond the simple calculation. These unknown properties, the more detailed properties of exoplanets, lead to a substantial amount of uncertainty as to declaring how many exoplanets have been found in the habitable zones of their parent stars. But with the Kepler haul of nearly 4,000 exoplanets, it seems that several hundred are in the habitable zones of their stars. And in one system, 3 have been found.